with us, right? He has a very impressive track record in terms of publications from his PhD thesis, published in all high impact journals. And then one of the key approaches he used was robust optimization. And I felt that it would be good for us to have this session where he teaches it himself. Okay, Dr. Oladimeji, over to you. Thank you for joining us. Are you there, Doc? You are muted. I don't know if you're speaking.
Oh, can you hear me now?
Yes, we can.
All right. Okay. All right. Once again, good morning, Prof. Thank you so much for having me here. And then good morning, my colleagues as well. I believe by now it should be around 2 p.m. in South Africa. So it's great to be together again. So I'll be taking a tutorial on robust optimization, and I will be using a case study on AIMMS. I'm sure you might have heard of this before. And if this is your first time of hearing it, we will just do some works together today. So basically, robust optimization has to do with moving from a nominal optimization that many people are accustomed to or are familiar to a model that survives uncertainty. So as we go on in this presentation or tutorial, we'll be understanding what uncertainty means and how do we encounter it, in most of the works that we do, right? So, so it's going to be something very short because robust optimization is a very, very broad field, very broad. And when I was doing my PhD, I came across a textbook on robust optimization, and it was, a very big one. So we have a lot of researchers in the field, a lot of publications have been done, on it. So these few hours that we have together, we might not be able to cover extensively, on the A to Z of it. But we will try as much as possible to stimulate our interest, and get basic understanding, from it. For as many who would love to use it in their research work or in their projects, with the time that we have together, we'll be able to unpack some things in it. So, and then we will look at AIMMS fundamentals and tutorials. Now, one thing about modeling, basically, and robust optimization as an example, is that you get to do some mathematics on your own, you get to do some modeling and some things on your own, and then you apply or you use softwares, like MATLAB, like what do you call this, Python, C++, and so on like that, to code what you have modeled. Now, the advantage that MATLAB, C++, Python, and the rest have is that you have flexibility in your coding, right? But you also have, a lot of work to do. Now, the advantage that AIMMS bring into place is that in as much as you understand the syntax of AIMMS, you can be able to, within the environment of AIMMS, do whatever you want to do. And you construct your model, your objective function, your multi-objective function, your constraints. You do all of those things within the environment of AIMMS, which makes your work easier than if you have to do it from the scratch, right? So we look at AIMMS fundamentals, and then we take a practical demonstration to help our understanding. Now, basically, we'll start with optimization. We'll go to robust optimization, and then we will try and I have two screens, please. One screen to present my slides, and then another screen to write some things on the whiteboard. And if at any time you have a question, just kindly interrupt and let me know your question, and then we'll take it together, and then we'll move on from there. So optimization is applicable in our daily lives, even, in our businesses, in our research, whatever we do, optimization is applicable. Whenever we engage in any activity, we want to ensure that the activities or the tasks are done, within the shortest period of time. We don't want to waste any time unnecessarily. We don't want to waste any money. We don't want to incur cost unnecessarily, right? So what helps us to achieve this is optimization. You have, for example, a supplier who has, different customers in different part of the country or different part of the world. And these customers are requesting for certain quantity of goods from the supplier. The supplier has to ensure that these goods are delivered to these customers, right? And minimal cost is incurred, minimal risk is incurred in delivering those goods to those customers. Maybe he has to go through the part of the least resistance, he has to do all of those things. Those things are under optimization. As a matter of fact, an example that is kind of very close to us as energy engineers is you have different energy generation stations. You have solar, you have wind, you have hydro, you have natural gas, you have biomass, you have a lot of them. And you want to supply the community, you want to supply customers with these sources of energy. It is electricity that, all of these stations have produced. However, you have to consider a lot of things. You have to consider the cost that you will incur, in transmitting or distributing this electricity to the customers. You have to look at, the environment, which will not cause environmental degradation among the options that you have, which is more reliable. You have to look at different criteria, different options, and out of this criteria that you have, you rank all the power sources, and then out of the feasible options that you have, you'll be able to say, this is the optimal choice. This is not optimal based on this, based on this, based on this, right? So you have, so this optimization helps you to make optimal decision, not just like you have your cake and it's not like you're going to have all the benefits, right? But it helps you to get the best choice out of all the options that you have. Now, basically, optimization model has some components. It has 4 basic components. It has the objective function, it has the decision variable, the parameters, the parameters and the constraints. Sorry, this is meant to be the last thing here is meant to be constraints. So it has the objective function, the decision variables, the parameters, and the constraints. And here I have a grid-tied solar PV system. So what I have here is more like, a grid-tied solar PV system that has all the protection devices, the DC disconnect, the combiner box, the AC disconnect, the main panel distribution, but it has all of those things. Whenever you are modeling, you try as much as possible to simplify your model. So when you check some articles or most articles on PV sizing, renewable energy system sizing, they don't put all of these protection devices there. They just, simplify it by making all the protection devices and the converter to just be the energy management center. right? So in this solar PV system, we have solar production, from the solar panels. When the solar production is higher than the demand, the demand is met and the excess is sent back to the grid. Is sent to the grid. When there is no production from the solar panel, or the production from the solar panel is very low, then we have input from the grid to support what has been generated by the solar PV system, and that is used to accommodate the load, right? So the grid serves like the battery. It takes in whenever you have more, and it releases whenever you don't have so much. And then the optimization model for this kind of system is displayed in this place based on some parameters, right? So you have the objective function. When you have just one particular criteria that you want to optimize, optimization can go in two ways. It can go in maximize or minimize. So if you have just one objective function that you want to maximize or minimize, we call that a single objective function. When you have two or you have three that you want to optimize, maybe, for example, now, in this particular optimization model, you have just the cash flow. You have just the cash flow, and then you also want to consider reliability. You want to consider some other, criteria, not just the money alone. You want to consider the environmental factor, how much of carbon emission is saved from the environment. You want to do all of those things. So you have multi-objective, different objectives, and then you set your weighing criteria to it. That is the first component of optimization model, the objective function. Then you have the decision variables. Those are the variables that you can change based on whatever you want from the decision, from the optimization, and from the objective function. So here you have the number of PV panels, the input from the grid, the export from the grid. Then you also have the parameters. Those are known values. For the decision variables, they are not known values. It is the optimization modeling that will give you the value of the decision variables. But for the parameters, these are known values. They are the ones that you put into the model, like the cost of components, the prices of this, and stuff like that. Now, when you are doing uncertainty modeling, it is the parameters. It is the parameters that are subjected to uncertainty, not the decision variables. It is the parameters. So we are going to, when we go deeper, we will understand better. Then we have the constraint as well. The constraints are the conditions that must be satisfied. You have to set constraints. Otherwise, your model is just going to give you, if there's no boundary, you don't have, it's just going to give you, any values. But if you set constraints, or even give you a feasible solution, but if you set constraints, it tells you that, oh, this must be satisfied for my model to work. And these constraints are obtained from the working strategy of your system. So you have to understand your system. You have to know how your system works. And then when you understand the way your system works, then you'll be able to mathematically represent, the way it works, and you put it in the optimization model. So, for example, now if you look at what I have here for the first one, the power balance constraint, it tells you that at every point in time, the power production must be must be equal to the demand and then the export to the grid. Then if you look at the second and the third one, it has to do with you cannot have the grid import and the grid export at the same time. It's not possible. It's either you have the grid import or you have the grid export. So you can't have them both at the same time. So all of these things are things that you have to understand from your system, and then you put them into the model. Then you understand the nature of data that you are dealing with. For example, for my decision variables, our NPV here stands for number of PV system, number of solar panel. Now, it's not possible for you to have 3.5 solar panel. You can either have, you have integer. You can either have 1, 2, 3, 4, 5. The number, it's an integer. It is not a free data, right? So if you have, so you have to set the kind of data that NPV is going to be. You have to set that it must be a whole number, an integer. You have to put that in your model as well. So this is the way one represents, or one displays or an optimization model. So this is just an example that I have just put here for us to understand what optimization model is. Now, we've understood the optimization model. Now, let's talk a little bit about robust optimization. As I said earlier, when I was opening the tutorial, most of the time when people are modeling, they model with fixed number. They model with an exact number of, parameters. And because of this, they do not give room for uncertainty. They do not give room for some inexactness. It affects the solution of the model. Take, for instance, here I have two conditions. I have this, which is 2.541x1 plus 1.4132x2 plus 10.5234x3 is less or equal to 10.41. Now, this particular equation is, the boundary for this equation is this place. Please follow my cursor so that you can understand what I'm saying. Is this from this red down, this way to this. That is what this solution represents. Now, I just changed the 5 here and the 5 here, the 5 in red color, to 7 here and to 8 here. Just 0.3 change. I increased the 5 to 0.2 and 0.3. I increased the 5 to 7, 2.5 to 2.7, and then 10.52 to 10.82. And because of that, the boundary of the solution has changed. So it means that what was optimal in the first model or the first equation is no longer optimal in the second one. For example, here, before the change was applied, any value I have here is optimal. So if, for example, I have a particular variable and the intersection of the variable is here, the solution is optimal, but just a little change, when I put the same point, it will no longer be optimal because this is the new boundary for the solution. This is the new boundary. It's no longer optimal. So just a small change, it has changed the whole solution. And as men, we are prone to errors, maybe error in measurement. Even for the best of forecasting techniques can have some errors. Natural phenomenon like the example we looked at the other time, which is energy from the sun with energy from the grid. It is possible that the amount of solar irradiation that you get yesterday is different from the one that you get today. And because of that, if you model the solar PV system based on a particular value of irradiation, you will end up having issues. That's why sometimes when people they install solar panels in their home, they expect a particular number of a particular value, in the energy production. And after some time, they do not see that simply because when they were designing it, when they were, sizing it, they didn't look at some important considerations such as degradation, the changing value in the irradiation and some other things like that. So it's very important that we consider uncertainty whenever we are optimizing. Okay, so here I'm going to write so that we can understand clearly what I'm talking about. So here it is about building uncertainty set types in AIMMS or in robust optimization. There are different uncertainty types that exists in robust optimization. There are a lot of them, but these are just the basic of these uncertainty set types. And this is what determines the behavior of the uncertainty that you're dealing with. For example, we have the box or the interval uncertainty. And let me just write here. For example, we have this graph. This 1, this -1, this 1, -1.
Where are you writing? Are you still writing on the slides or writing elsewhere? I can only see your slides.
I'm writing on the second screen.
You can't see that one. Or maybe am I the one that
writing on the second screen? Can you see my? I have two screens. I'm sorry, I couldn't get a way to write on the slide. So if you can check the second screen, that is where I'll be writing. And can you see it?
No.
No, we can't.
You can.
I think you need to stop. We can only see one screen per time. So I think you need to stop sharing this PowerPoint and then now share that one.
Yeah, that's okay. That's true. Costs.
Yes, we can see
Okay.
your whiteboard now. So I think you just need to it's a pin, but I think we just need to alternate.
Thank you, sir. So here we have, so I'm discussing the box or the interval uncertainty. And this is the way it works. This is Z, Z1, Z2. This boundary here that is defined by -1 is lesser or equal to Zj, lesser or equal to 1, where J is 1 to n. So it means that whatever, if you use this kind of uncertainty set types, it means that whatever solution you are going to, whatever uncertainty value that you use within this box, the solution is going to capture it. It's going to capture it. As against, you just have like a 1 point value for your parameter. If you just have a 1 point value for your parameter, maybe just 1 point like this. Let me draw another graph so that we can understand what I'm saying. Maybe you just have a point like this, right? What it means is that whenever you are optimizing, your model only considers that parameter to be just 1 point, which is just here. But if you adopt uncertainty, robust optimization, and you adopt box or interval uncertainty, it means that any value you have within this boundary, here, wherever you have it, the model will be optimal. It will give you a solution that aligns with the values that you have here. If tomorrow now, let me go back to this example I gave you. If tomorrow now, the point that you have here is no longer here, it is here, the solution that you provided will fail because the point has changed. Whereas if you used robust optimization and you consider uncertainty, before your point was here, if tomorrow your point comes to this place, it is going to be, your solution is going to be optimal. It's going to account for that failure, that uncertainty. Let me give us an example. For example, the example of the solar irradiation I gave before. You want to size a solar PV system based on time series data. Maybe you want to use 1990, year 2000 to year 2000 to year 2010 to year 2020. This is the year and this is the irradiation. And the value for this was 150, here 170, here 198, and here 164. Now, many people, what they will just do is that they will just find the average. They'll just find the average of these 4 values. This time series data, they find the average. And so who can give me the average of this thing? What's the average? Can you please punch your calculator on your phone and give it to me, please?
$171.5.
171.5. Thank you, sir. All right. So now let us do something. We have this. The lowest here is 154. The highest is 198. And then we have 164. And we have 170. Right. Now, for somebody that used the average, what the person is saying is that somewhere here where we have 171.4, at this point, this is the value of my parameter, just here. Just 1 point. Now, if he decides to go ahead with the optimization of the system based on an average value of 171.5, if tomorrow the value comes to this place, maybe 168, whatever results he has obtained based on 171 may no longer hold, because he used a 1-point value of 171.5. Now, the advantage of box uncertainty type is that it gives you the opportunity to consider whatever value falls between 154 and 198, maybe 160, maybe 180, whatever value it is. The solution is so robust to accommodate it. So here we can have 154 is less or equal to I, and I is less or equal to 198. So within this, it gives you the opportunity to have whatever irradiation within this boundary. This particular solution is fine with it. It will not shake. But if you just use the average value of 171.5, it's going to have issues on the long run, or in the long run. So that is box uncertainty sets. It gives you the opportunity to have your values within a box. And as long as the values are within this box, your solution is optimal. Now, the advantage of this kind of uncertainty type or uncertainty set type is that it is very easy to compute, but it is very conservative, very, very conservative. The problem with this is that what the advantage of this is that whenever you have your optimization model that is linear and you inject uncertainty to it, the robust counterpart is still going to be linear. But by the time you go deep into some other types of uncertainty set type, you might end up getting a robust counterpart that is not linear. So that's one of the advantage of this kind of uncertainty set type. Now we go to the second one, which is the budgeted. For example, we have this boundary. We have one here. We have one here, -1. We have one. We have -1. So this is more conservative than the one that we had earlier. So whatever value falls within this place, the solution is fine with it. And then we have Z1, Z2. So this shows that Z absolute is lesser or equal to 1. And the summation of Z absolute. So for this one is 1. If you have something like this, a boundary like this, let me remove this. Let me put 2 there. Then this becomes 2. If you have something like this, it's in my slide, but I can't show my slide now. Just bear with me, please. So this is 1.5, right? So there are different types of budgeted uncertainty type, different types, different configurations. So basically, whatever value falls here, for example, now, if I'm just using the value of for the one that is 1, whatever falls within this place is not captured. It is whatever falls within this boundary that is captured. So then the next one, the next type of uncertainty set type is the ellipsoid. It's the ellipsoid. So whatever you have your graph, Z1 and Z2. So whatever value, if you have scattered values, ellipsoid captures all the values. So whatever value is within this, the solution accommodates for it. The last one here is the convex hull. So we have different types. We have this, scattered around different values. What convex hull does is it joins the external points together. So whatever point is within this, solution is optimal for it. So there are other types of set types. These are just, some of them. We can do well to make further research on it. I don't know if so far, if there's any question. Do we have any questions so far? Any questions so far? Before we move on to
Please ask questions now. So before we go further, I know many of you are doing optimization and will benefit from this. So ask questions. If there are no, Doc, continue. I believe they are following, although it's quite easy to follow at this time. Yeah.
Sorry, I have a question.
All right.
Yes, look, you talked about the import and the export.
What?
You talked about the import and export.
Yes.
Of energy. And
yes.
If you have a complex system, there'll be some plants that will be generating power into the grid, and some other plants also are importing power from the same grid. So I could not get it clearly. Then there's a book you talked about on optimization, but you didn't give us the title of that book. Thank you.
Okay. I was just it was the book on optimization. It was just it was in passing. So I can check my folder. Excuse me. I can check my folder and send it across to you, or maybe Prof. If anybody would love to go through it, I can send it across. Then for the case that you talked about, this is just a very simplified case for one generating system, which is just the solar PV system, right? Now, if you have different energy systems, you have the wind, for example, for instance, you have the solar, you have the wind, you have the biomass at different points. Now, each of these systems, we have the import variable and the export variable. Each of them, like for the solar now, it has the import variable, it has the export variable. For another system, it has the import variable and the export variable. For the other one, it has the import variable and the export variable. So it does it in such a way that when the system is importing, it cannot export. It cannot export back to itself. It can only import. And anytime it is importing, it cannot export back to itself. Now, if you understand the strategy or the operation of your system, then you can write a mathematical equation that aligns with the strategy of the system. For example, in the case that we have just talked about now, it is basically that import and export is just as we have a battery now. A battery can discharge or discharge. You cannot have a discharge and charging at the same time. The battery can either charge or discharge. So you can write an equation that gives us that kind of operation that, oh, at this time it is discharging and at this time it is charging. Anytime there is charge, there will be discharge. There will not be discharge, sorry. At any time there is discharge, there will not be charge. So you can write an equation, that talks about that kind of operation. It is very possible. So, and that is the example that we did here. So for the one that you talked about, is a complex one, but when you are able to highlight the operation of the system, you can write an equation that describes that particular strategy. I don't know if I answered your question.
Yes, you've answered. Thank you.
You're welcome. So let's move on to an example. There are a lot of mathematics that goes on in this optimization. I don't want to bore with the mathematics. We can, if you have interest in learning optimization, you can read more about the mathematics of it. So from the textbook that I'm going to send across, it will also be useful for you to be able to learn one or two things from it. So let us look at a particular case study and work it together. So here we have, it says 7 plants, plant 1 to plant 7 to be 7 products, product 1 to product 7
So
to be manufactured.
Which screen are you sharing?
I'm sharing my slide.
Can't see it.
I'm sharing my slide.
And now we can. Thank you.
Okay. All right. So we have this case study. 7 products, product 1 to product 7 are to be manufactured on 5 machines. Machines 1, 2, 3, 4, 5. Now, the unit profits of the products are presented as well as the machine usage in the table that we have below. The total time to be spent on the machines per planning should not exceed 192 hours. So here we are asked to obtain the maximum profit for the investment based on the following conditions. Number 1, exact values of the processing time. So this is the processing time that we have. This table here, we have the machines 1, 2, 3, 4, 5, and then we have the product 1, 2, 3, 4, 5, 6, 7. Now, if you are to manufacture product 1 on a machine 1 kg of that product on machine 1, it takes you 0.5 hours to be able to do it. If you are to manufacture or produce product 1 on machine 2, 1 kg is going to take you 0.1 hour. Same for product 1 for machine 3. 1 kg of it is going to give you 0.2 hours. So the same like that. Here, the same thing for product 2 for machine 1, product 2 for machine 2, product 2 for machine 3, the same like that. So this is like the number of hours it takes to produce 1 unit, 1 kg of the product. And here, this table, we have the unit profit. If you have product 1, the profit for 1 kg is $7. If you have product 2, the profit for it is, for 1 kg is 6 hours. I mean, it's $6. And then you have it like that to product 7. Now, they asked in the question that is the exact values of the machine processing time. So this is the exact value: 0.5, 0.1, 0.2, 0.05, 0, and so on like that. That is the exact value. Now, what determines the usage of machine? What determines, the amount of hours they are going to spend on a particular machine? The speed of the operators. If there's any fault that needs to be dealt with, maybe the machine breaks down and the technician has to come and do some works on it, right? So all of these things cannot be determined exactly because it is not fixed. So there could be some deviations from the exact value because of some unplanned occurrences. So because of that, the upper value, so there will be some uncertainty, but you can cap it. Like the upper value, if you look at the second question, the machine pressing time perturbates forward and backward by 0.01. So it means that the machine time can either increase by 0.01 or can either decrease by 0.01. In a situation where the machine operator is very slow or there's an issue with the machine, then there could be an extensive amount of time. And in the case where there is no problem and the machine operator is extremely fast than usual, then we have a lower pressing time. So in that case, in this case now we are dealing with uncertainty because it is not just 0.5 now. It could be 0.501. It could be 0.5. It could be 0.5005. It could be 0.4995. It could be 0.4998. So a lot of things, are going on in between. So here, for both cases, we are asked to find the maximum profit for the investment. Now you can apply this to energy systems. You can apply this, to HVAC systems. You can apply this to anything. Once you have the understanding, the basic understanding, it can be applied to other kinds of systems. I don't know, do we have any question on this case before we move on to the solution? Okay, so let's move on to the solution. I will stop sharing here and then start sharing on my whiteboard. Can you see my screen now? Okay.
Yes.
All right. So from the question that we have, the first thing that we do is to set the indices. Now we have first the machine and the products. So let's say P stands for the products. So we have product 1 to 7. So we have product 1, product 2, product 3, product 3, 4, 5, 6, 7. And then we have the machine, which is just from 1 to 5. These are the sets. So here, this P, anywhere you see P, you know you're talking about the product. Anywhere you see M, we're talking about the machine. And then the next one is the parameters. Can somebody just help us from the question I have put on the screen before? What do you think are the parameters from the question based on how I've defined parameter before? What are the parameters? What stands as a parameter in the question? Anyone? So don't forget, I gave 4 tables. 3 tables are talking about the same parameter, while the 4th table is another kind of parameter. And then in the body of the question, there is also a parameter that is given, which is the total available time on the machine. Can we remember? So let's say our HM is a total available time on the machine, which is 192 hours. Then we also have the unit profits. So we're given. This is 192 hours. We need to put a unit there. The profits per kg. And the unit is dollars per kg. So I have CP here. So it means that this C is indexed in P. Can somebody tell us what that means? Anybody? I have CP, and this, I said this C is indexed in P. Can somebody help us with that? What does that mean? Anybody, just try.
Where are the guys using AIMMS? Chima? That's Chima here. A couple of you are using AIMMS.
For those who are using AIMMS, and even people who are, if you are familiar with optimization, you should be able to say 1 or 2 things about this. Just try. Yes, please.
Okay, I feel it's the profit per kg per product.
Okay.
That is, you have C1, something like C1, C2,
C1 to what?
C3, C1 to C7.
Thank you. Thank you so much. That is correct. So you have C1, you have C2, you have C3 to C7. So this C1 stands for the unit profit for product 1. C2, unit profit for product 2. To C7, unit profit for product 7. That's just it. Thank you so much. Then the next parameter that we're going to look at is, let's call it this, APM, and that stands for the duration. The duration or the hour it takes to produce or manufacture product P using machine M. So again, who can help us with what this APM means? Don't forget that P is 7. The dimension is 7. And M, the dimension is 5, right? So so here are the 3 parameters. It's very important that you set out all of these components. They set the parameter, you set everything out before you start, it will help you when you are modeling, when you are writing out the mathematical stuffs, it's going to help you. Then the next thing we look at is the variable. The variable are the unknowns, the variables. And what are the variables here? Number 1, we have the quantity of the product, the product quantity. So here it is also indexed to P, so it's going to be to 7. And then the total profit. So the next thing is the constraints. The constraints. From the question, who can tell us what do you think the constraints are? There are just 2 constraints. And who can give us an idea of what the constraints could be?
I think one constraint is the amount of time you can spend on a machine.
Okay, which is, the limit is what?
192 hours.
192 hours. Thank you. That is one constraint. What do you think the second constraint could be? That's this one is very, very important. What do you think the second constraint could be? Who can help us with that? I talked about data types initially. Data types. What kind of data do we think our XP is? There's a question here.
No, it's an answer. She's suggesting the second constraint. It's actually an answer.
Sorry, yes, sorry, yes, Prof. I was just giving the second constraint.
The budget to produce the project, the products, right?
Your question was, what is the second constraint?
Yes.
So she is saying that budget is she's seeking that's an answer.
Okay.
With the question mark for you to determine if it's correct, if it's right or not. Yeah.
Okay. This one is actually the parameter, because if you look at the table that was given to us initially, this one here, we have a table. We are given two tables. This for this table here, and this table. So this one tells us the time it will take to produce 1 kg of products in each of the machines. So maybe what you said relates to this, right? Yeah. So initially when I was talking about optimization, I talked about the data types. And that's very, very important, because if you do not set the right data types, you will get a solution and you will think the solution is right, whereas it is wrong, simply because you have not set the right data types. There are different types of data. We have the binary data, which is just 0 and 1. We have the free data. Free means that it is minus infinity to plus infinity. We have the integer, which is just the whole number, 1, 2, 3, 4, and so on. We also have the non-negative. Non-negative is any number that is not negative. 0, 0.1, 1, 2, 3, and so on like that. And we have non-positive, which is, minus, it is in the negative. So for example, now this XP, which is the quantity of the product, it's in kg, while this one is in dollar. We have to set this to non-negative. That is, we say that X1, X2, X7, they must be greater or equal to 0. That is how to mathematically represent that a data is not negative. It must not be negative. You can never have a negative mass. You can never have minus 2 kg or minus 3 kg. It will always be positive. So if you do not set that into your code, into your model can assume any value, any kind of data for this particular variable. So you can assume negative for it. You can assume anything. So you have to ensure that you set it in the right way. So you don't have to now. Pardon? Excuse me. Now you don't have to write x1, x2, x3, x7, x to x7, you don't have to write that. You can just do a compact form. xp is greater or equal to 0. That is our first constraint. It tells you that our value of xp must never be negative. So for the person that asked me about complex energy systems earlier, it is about you, whatever you want to describe, you have to describe it mathematically. So this is an example. You want to say that a value must never be negative. Then this is how to write such a thing. Now, the second constraint, which is what somebody told us about the time limit. We were given a table of 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 5, 6, 7. We were given a table earlier, if you remember. Remember that table that we were given in the question? So here stands for A11. Here stands for A12, A13, A15, A71, and A75. Now they are saying that this is for machine and this is for products. They're saying that anytime you use on this machine, the limit is 192. The limit is 192. The limit is 192. 192. 192. You cannot go beyond that. So who can tell us how we can represent this mathematically? This is going to be the last thing before we move into how to program it. Who can give us an idea of how we can write this? If I want to say that, I want to write that for machine 1, I cannot go beyond 192. I cannot go beyond 192. And what I have here is the time is going to take to produce 1 kg of products. The time it will take to produce 1 kg of product, time it will take to produce 1 kg of product, and so on like that. So we can give us an idea of how we can represent that. Okay, for machine 1, I cannot go beyond 192. Just give it a try.
Okay, 0 less than A.
0 less than
A and P.
A.
A subscript NP.
Okay, that's APM, all right.
APM, sorry. Less than 192.
Less than 192. Okay, is that all? Okay. There is something missing here.
I can,
Yeah,
can also try.
thank you for
Less
that
than
input.
equals to. Can say less than
Let
Less
me
equal
than
to.
equal. Okay, thank you, but there's something missing here. For example, now we said let's even check this out ourselves. 192 hours, right? And this one is hour per kg. So can we see that there is consistency is not there? So you could just add APM XP. Good, less or equal to 192 hours. And you put summation P1 to 7 for all values of M. Is that clear? Okay, let me break it down for us so that we can understand better. Now I have 192 hours here. I am to ensure that I'm using this machine 1 and I must not exceed 192 hours. What it means is that I have A1 X1 plus A21 X2 plus, I will do that to A71, right? X7 less or equal to 192. So I'm going to do that for the second machine as well. A21 X1, A22 X2, the same thing like that. So I'm going to have how many equations? I'm going to have 5 equations for the constraints. So instead of just having, that's too much. So we can have it in a compact form, which is, this stands for APM or AMP, whatever you want to call it, XP, and then 192. So P is equal to 1 to 7, and then for M is 1 to 5. So with this now, you have been able to compress the 5 equations into one. So these are the 2 constraints that we're going to have, and then we can once we have the optimization model complete, then we can now solve it. So at this point now, do we have any question or anything that we need to clarify? So at this juncture now, you can choose to use AIMMS, right? The model that you have, the mathematical model that you have done, you can input them into AIMMS. Or if you want to use Python, MATLAB, and some other programming languages, you can also use it. So you have to convert that mathematical model to the language to the way that mathematical language understands it. So, but before now, you cannot do anything unless you are able to mathematically represent the model that you want to do. So before we go on, I'd like to just give us the way the robust optimization is going to look like, because I want us to do both of them together in the AIMMS. If we look at the question, we were told that there is a forward and a backward deviation of 0.01. So let's assume that mu is the deviation, whether forward or backward, and Z is the uncertainty factor, right? Now, it was only the APM that is subject to uncertainty. So we write APM plus mu Z. So this becomes the new parameter because we have injected uncertainty to it. Now, for example, for the example that we had, we said mu is 0.01 and Z, is 0 is less or equal to Z is less or equal to 1. Sorry, it's -1. So -1 is less or equal to Z, less or equal to 1. So if for example, if your Z is -1, it means that APM and if a Z is 1, it means APM. So you have these two limits. You have these two limits. So this is what you are now going to. So this is what you are now going to put into the equation that you have. So earlier we gave these constraints: APM, XP, so this particular parameter becomes this. So you put this there. You can choose to leave it like this, or you open it up. But so you want to change. It was 0.01 before. You want to change it to something else, maybe 0.02. You can do that. This one is always, it doesn't change. Who can tell us the uncertainty type that is used here? What is the uncertainty type, uncertainty setup that is used here? The uncertainty set type that is used. Who can remind us? We dealt with it earlier. Anybody? Box or interval. If we want to use something, maybe we want to use ellipsoid, it becomes something else. But we cannot use ellipsoid for something like this because it's just one dimensional. If it is two dimensional, then we can use ellipsoid. So we can't use, it's just one dimensional. It's just you go forward or you go backward. You don't go sideways. So that's why. So we use box for this, and it's very, very simple. Okay. Let's go to the use of AIMMS to bring out this. I will stop sharing here and then okay, can you see my screen?
Yes.
Okay, so we want to use AIMMS now to solve the model that we have, right? So when you click on the AIMMS icon. This is what it brings out for you. Then you create a new project. I might have to, okay. So you create a new project, whatever you want to call it. You also want to call it exercise. Press OK. So the first thing you want to do in AIMMS is to put in your identifiers. Your identifiers are what we talked about earlier, your sets, your parameters, your variable, your constraints. So you want to do that. So how many sets do we have in the question? We have two sets, right? We have the product and we have the machine. So we have the product. Let's put in the product. You have the machine. Then, okay. You set the index for the product. You want to use P as the index. And then when you've done that, you go to check and commit, or you may want to use check, commit, and close. What check means is that you want AIMMS to check whether your syntax is correct. If your syntax is wrong, AIMMS is going to tell you to correct where your syntax is wrong. For example, now let me just put dot here after P, and let me press commit. It's telling me something. I've pressed commit. I mean, I've pressed check, and it's telling me that there's something wrong with what I have written. So if I remove the dot and I pressed on check, it's going to pass me. And commit means that you are telling him this is what you have put inside the set, and you want to close it the normal way you close your work. So even if you are wrong and you press check, commit, and close, it's going to tell you that something is wrong. But if what you've done is right, it aligns with the principle of AIMMS, it's going to pass it. So it's going to pass it. Let's check. Yeah, it did. So you have our machine, and then you want to use hem as the index. So the same way, let me just try and put dot here, and I press check, commit, and close. It's not going to. So I have to correct it. So the next thing is I have set my product and my machine. So you want to go in, what are the things that makes up the product? We have product 1, 2, 3, 4, 5, 6. So you want to put that inside this set. So you just type product 1, and then you press enter. Then product 2, enter. Product 3, product 4, product 5, product 6, product 7. That's closed. And then the machine, the same way we did here. You want to use this, you want to use data, or you want to come here and right click and press data, and then you have machine 1, machine 2, machine 3, machine 4, and we have that. So we can check, commit, and close. The next thing is the parameters. Here we have, how many parameters do we have? We have 3 parameters, right? The first one is the total time available. Time available. Time available is just a floating number, just a single number. So you cannot index it to anything, right? So is 0, but if you declare the value, you declare the value to be 192. And then you check again, it becomes 192. You check, commit and close. And then we have the profits, the unit profits. Unit profits. The unit profit is indexed to P. It's indexed to the products. Products 1, 2, 3, 4, 5, 6, 7. So this is how you are going to do it. After you have set the name, you click on the unit profits, and then you give it the domain is P. So you come to the index domain and you put P there. Now, before I do that, let me show you us something. If you do not put anything there, it's just going to be a single number. But by the time you put P there and you check and commit, then it becomes this. Why? Because you already indexed it to P and you have already set the P before, the product before. So then the next one is the duration, the number of hours it takes to produce or manufacture product P using machine hem. So let me just use duration here. And the duration is indexed, the index domain is both P and hem, not just only P. Now let me show something. If I use only hem, it's just going to give us this. But if I use P and hem, we have something like this. So that is the duration. That is those are the parameters. And then we want to look at the variables. And then we look at the constraints. They are arranged here on top. So we want to look at the variable. We want to look first at the quantity of the products. So here, the quantity of products is in P domain. So we put P there. And what kind of data is it? Is it free? Is it non-negative? Is it non-positive? Is it binary? Is it integer? Whatever it is, you have to put it. So it is non-negative. It is here, this. Then the total profits. Total profits. I need to check and commit. Yeah. Total profits is free because somebody can lose and somebody can gain based on the decisions that you've put in the model. So that's free. It can be negative. It can be, if it is positive, that means that you have gained, and if it is negative, then it means that if it is positive, you've gained. If it is negative, there is a loss there. So how can we what is the way to write the profits? How can we write the profits? What's the way to write the profits? Anybody wants to help with that? But the profit is the product of the unit profits and the quantity of products. That is the way to write the total profit. So you have profit from product one, which is quantity of product times unit profit. For product 1, 2, 3, 4, 5 to 7, you add them together. So basically you have this. So you want to check if what you've done is right or not. If it's right, it's going to. So after that, we have the constraints. So here we're only going to have just one constraint, which is we've already declared one constraint in the data type that we used for the quantity of products. So here we want to declare the last and the second the constraint, which is the time constraints, the time limits. So here from what you have said, we said that for the duration, quantity of products. Then for all hem, so you put the hem here as the index domain. And I want to check and commit, and I wait the response of AIMMS, check and commit, and it's telling me there's something missing. The definition of constraint time limit is not a restriction. Perhaps a comparison operator or a variable is missing. So normally when you're talking about constraints, there should be equal to, greater or less than, those kind of thing. That is, you are limiting, you are constraining a particular characteristics. So, and I didn't put that there. So I should. The time available. So after this, we have to check. So everything is fine now. So we go to the how to execute it. That's the next thing. So and here we have solve. If you want to, you go to the main execution. If you want to solve, you go to the main execution. Then you put before that, we go to mathematical program. And that mathematical program, we want to maximize profits. So here we choose the variable that we want to optimize. We want to optimize total profits, right? And what direction are we going? Do we want to minimize total profit or we want to maximize? So we'll do that here. Yes. Then we check and commit. And then we go to come here, solve, and maximize profits. So we check, commit, and close. So everything is fine as far as our model is concerned in AIMMS. So the next thing is for us to impute the values, the parameters. So the time available. We already have 192 there. The unit profits, we have to impute the parameters for it. So let's go to where we have it. We can just copy and paste. The duration. So those are the parameters. That's where we need to put values into. Okay. So far, do we have any question? So we compile. Before I want to show something. Before now, it's 0 because we have not done the optimization. After the optimization, it gives us the value. That is 9,600. That is total profit. And the product, so not all products will be manufactured. So it selects the products to manufacture, which is products 3, 4, and 5. Those are the products to manufacture. Since we have the liberty to manufacture any products, the limit we are given is that the time must not be more than 192. We have limit 1. Then limit 2 that we're giving it, of course, is that the product is non-positive. I mean, yeah, it's not negative. It means that it has to be, kilogram it can't be negative. It has to be positive. So that's why we have 240, 640, and 640. So this is the best choice in terms of maximizing your total profits. And this is the maximum profit that you get. 9,600. Now, if you want to go with the robust optimization, let's quickly go with that. I'm going to show us 2 methods here. The first method is how to solve it using using this approach, and then how to use AIMMS robust optimization add-on to also solve it. I said earlier that when you have your deterministic model and you want to subject it to uncertainty, if you have your uncertainty data set to be linear, the robust counterpart that you're going to get will also be linear. But if you have some, you are using some complex data sets, complex uncertainty sets, you might end up having a robust counterpart that is not linear. So, but in this case, we used our interval or the box uncertainty data sets. So because of that, our optimization is also, our model is also linear. So I will show us that, and then I will also show us how to use the ideal robust add-on in AIMMS to be able to do it. I don't have the license, so I cannot run it, but I will show us how to do it. I can run this one because my license is limited now. So I will show us this, and then that one I will show us how to do it, but I will not be able to run it. So that means we cannot compare the results, but the results will be the same if we do it on our own. So let's go back to the if we want to use the linear approach, we have to set two more parameters. We set the deviation. Don't forget when I was converting the constraints to include the uncertainty, I did something when I was writing the equation the other time. You should not forget. So we include that there. So I introduced two things, parameter and then the uncertainty factor. So deviation, which I said is from the question, is 0.1. And then the uncertainty factor, which is 1, because 1 makes the decision worse. And the objective of robust optimization is to prepare for the worst case scenario. So you use 1. And then we go to the constraints. We had that there. We had deviation multiplied by uncertainty factor. So we commit. So the brackets are not expected. So we can remove the brackets. It's wrongly. So let's run it now. We go to where we have the profits. It's 960 for the deterministic model. Then for the robust, it is going to be should be so can we see if we look at the products, the values have changed. It's 239.999, 239.97, 239.97666, and so on like that. Let me check the model again, see where we can. If the deviation is 0.1, let's check. So we can see the total cost has decreased. That's decreased because of the uncertainty in the duration, the time it takes to work on the machines. We have put the worst case scenario that in a case where we have, we are spending more time, on each of the machines, it will result in a total profit decreasing. So here we can see that it has decreased by $3. Let's change the factor to 0.1. Can see it has decreased to 9,565. So the more you increase the degree of the worstness. The more you increase that, then your profit decreases. Before you said that, okay, the time it will take to work on the machine should increase by 0.1, right? Or decrease by 0.1. So the worst case scenario, so it affects the total cost. Before it was 960, now it has gone below. If you want to change it to maybe 0.5, so profits. So the more you increase the gap, the boundary, the space between the floor and the ceiling of the uncertainty, the more your total cost will decrease. So this is the first aspects for the robust optimization. So I will just use the AIMMS or robust add-on. Then that will be all on my side. So far, do we have any question? Any questions so far? All right, if there's no question, I would just please allow me to unshare, and then I will open the AIMMS for the robust add-on. Can you see my screen now?
Yes, we can see your screen.
Yes. Okay. So the difference between this and the one that we did, if you look at what's under the declaration here, this one, EP robust, I want you to take note of what I'm showing you. The EP robust, the upper bound, the lower bound, and that's all. I will show you something in this main execution as well. So that's just the difference, and I'm just going to run you through it. So before you, if you want to use the AIMMS robust add-on, the first thing that you do is to create an element parameter, and you name that EP underscore robust. That's the first thing, EP underscore robust. You put that. Is the one we just did now. So element parameter EP underscore robust. You put it there. And then you can see the range, you put all generated mathematical programs. You go to range, you go to predicted identifiers, and then you scroll down, all generated mathematical programs, then you put finish. Yeah. And the next thing that you do is the parameter that has the lower and the upper bound. That's the next thing that you check. So here now I have this duration has upper and lower bound, right? So I have property. Under property, I have stochastic, uncertain, and random. So these are the other ways we can we can solve for uncertainty in our systems, in our models. So you can use stochastic modeling, you can use other types. So this one we are going to use uncertain, and then okay. So under that uncertain is going to bring out this. Under this, you just put your box. Don't forget that we said that there are different uncertainty sets. We have the box or the interval, we have the ellipsoid, we have the convex hull, we have the budgeted. So here we have the box. So I'm using the box here. So in the box, you will now open the brackets. Because it is a box, the box has the ceiling and the floor. So you have both. You put for this lower bound, which is the ceiling, the floor, and then the upper bound, the ceiling. You put it there, and then so this is showing red because I have not indicated it here in my tree. So I have to go and then create two parameters. Lower, I'll just use lower. PM. And I will get another one again and I'll put hopper. All right. So you can check and commit. Box, it's not expected. Excuse me. Okay, this is supposed to be in the region, not in, supposed to be here. All right, so then let's go back to our total profits. The constraints. You have to remove this and just put it the way it is, the way it was initially. I'll put that. Right. Okay. So I haven't done this. The next thing we are going to do is we already have this. We already have this. Then we go to the main execution. I don't like. I just copy what I had. Copy this. This is what I'm copying here is also on their website, on AIMMS website. So you can always, all of this, these are kinds of quotes that they've written before, that aligns with their own software. So all that one needs to do is just to copy it and put it in one's program. Don't forget that this EP underscore robust has already been declared earlier. It's already here. So everything is from the website. And then just put it. So this is what we have. Right. So that's just called. So you put your, now we don't need the deviation and the certainty factor. They're not needed, so we can delete them. Right. So what do? We put in our data. We profits has not been declared. So it's not been declared. Okay, sorry. All right. So what we should have here should be the objective function, total profits. So let's check again. The MP is not referring to. So I think it's because I do not have the license, the robust add-on. I don't have it in this license. That's why it's bringing out this mathematical profit. Mathematical profit, yeah, okay. Let's do this. Okay, maybe not. Yeah. Okay, so so after we've done all of this, we just put the duration for the, this is for the deterministic, for the upper bound and the lower bound. We put that the upper bound is here. Is for the lower bound. So upper bound, the lower bound. So once you've done that, you check and commit, everything is fine. Then you run your model. So my license does not have the use of robust optimization add-on. So yeah, assuming I have the add-on, it's just going to give me the results. And we can compare it to what was done earlier. So there are times that you will have the opportunity to model your robust counterpart normally on AIMMS. If your if your model is linear, it's very easy. But in some cases when you don't have that opportunity, you can just use the robust optimization add-on. In my slide, I have the solution and then the links that you can use to access the materials and also their videos on YouTube. So do we have any question? That will be all from my side. If there's any question, we can entertain questions or any comments.
I have a question.
Okay.
Yeah, is there a way to carry out a sensitivity analysis to determine the tolerance of such robust optimization scheme?
If I would probe further, you want to determine the sensitivity analysis because of what? Why would you want to, and what kind of
tolerance gauge or such an optimization scheme? There a range through which it can fall through, or because you were talking about box, ellipsoid, I don't know if those things are kind of practical gauges or whether they are ways of determining the tolerance or
one of the things that, thank you for your question. That's a great question. One of the things that robust optimization helps to do is what sensitive analysis is going to do for you. Robust optimization can be able to carry that out for you. For example, for somebody who wants to, who has probably done a particular analysis and he wants to subject the result of the analysis. He wants to carry out sensitivity analysis on it. Like he wants to change a particular variable and know what the result of the analysis is going to be if he changes it. Maybe before you use the 0.1 and you give a particular result, he wants to change that to 0.2, to 0.3, to 0.4 and know what it's going to be, right? Now, what robust optimization will do for you is you have lots of tolerances. Maybe you have 0.1, 0.2, 0.3, 0.4, 0.5, and so on like that. Robust optimization can give you a solution that satisfies 0.1 to 0.4 at the same time. Now, for example, if you now have many parameters in that model that are subject to uncertainty, robust optimization can do that for you at the same time. Unlike sensitivity analysis that you can say, okay, I want to change this quantity at this particular time. And when I'm done changing this quantity, I will change the other quantity and, and so on like that. But for robust optimization and some other uncertainty analysis, you can put your tolerances for each of the parameters or quantity that you want to subject to change at the same time. And robust optimization will give you a solution that satisfies all the tolerances at the same time. I don't know if I answered your question.
Can I come in, engineer? I think you've answered it very well. The point needs to be made, like you said, robust optimization factors in uncertainty, right, inside the model, right? So the model accounts for uncertainty, while sensitivity analysis analyzes how the model, reacts to changes. You vary parameters, individual data points after you solve the model. Understand? So, for instance, you vary the total number of hours 192. For instance, you vary it to, you see what happens if you move it to 195, 200. How does it change your results? Then you now figure out the specific parameter that you have to be sensitive about, that it has the highest effect on your results. However, you can conceptually merge both, right? But in that case, it's now you're going to now basically change the boundary, of your uncertainty set. And I think that's what Dr. Oladimeji said. If you use -1 to 1, you can now, when you now want to see sensitivity analysis combined with robust, if it's needed, is when you are now saying, okay, you are now varying the boundaries, the range, some of the things, that those parameters, and you're now determining, okay, which data points for the boundaries of your robust optimization model do you have to watch.
Okay.
I don't know if I'm Dr. Oladimeji, did I?
Yeah. You're on point, sir.
Yeah.
You're on point.
No, you're the special guest.
Not at all, sir. You're on point.
I don't know the difference, because in that software, you say there's column for stochastic, there's column for random and uncertain. And I was like, stochastic, random, and uncertain, are they not the same concept, like the same thing? Or are there some slight differences? Like,
They are different. The stochastic optimization is different from robust optimization, even though they deal with uncertainties. Now, for the robust optimization that we talked about, we are looking at boundaries, right? We have the floor and we have the ceiling. So between that boundary, the solution gives you an optimal solution. For example, you have 0.2, 0.3, 0.4, 0.5, 0.25, So that solution gives you whatever is between 0.3 and 0.5, right? Robust optimization gives you the solution that satisfies. So even if tomorrow you change from 0.2 to 0.35, that solution still holds. If you change from 0.2 to 0.25, the solution still holds. Now, the difference between this and the stochastic optimization is that stochastic optimization deals with probability. Now, between the data range that you are considering, it does a probability distribution such that it works with whatever is like the likelihood of the occurrence. That is what stochastic optimization deals with. So when you want to work with stochastic optimization, you have to understand probability distribution, and then from probability distribution, then you go into stochastic optimization. So that does not deal with either ceiling or floor. It deals with all the data that is in that data set, the likelihood of occurrence of any of it. It takes it into consideration. For example, if you are optimizing a renewable energy system and you have a data set from 1990 to year 2020, maybe for time series number 1. For example, if you are working with time series number 1 to number 24. So for time series number 1, you have about 20 columns. For time series number 2, you have about 20 columns, like that. So what robust will do for you is that in that time series number 1, for example, and the other ones, it will give you the limits of the floor and the ceiling, and it's going to work with. So whatever irradiation that falls between the floor and the ceiling in that time series 1, robust optimization accounts for it. But for stochastic optimization, it works with the probability of occurrence of any of those. This is the way a simple way I can describe it. The probability of any of those points from number 1 to number 20 occurring. So if any of them occur, the model is robust enough to accommodate for it. I don't know. Do you get my response?
Yes. Like instead of choosing a ceiling and floor value, you choose a probability.
Exactly, of any of them occurring. So with that, whenever any value that is different from what you used in the deterministic optimization, whenever any value shows up, because that thing has been trained to accommodate any values from number 1 to number 20, it will also give an optimal solution. Thank you for that question. Do we have any other question or any comment?
Yeah,
you can add to what I've said.
Thank you for that wonderful presentation. I'm actually expecting to see some visualization, from the result presented. So is there any form of visualization on AIMMS software?
Yes, there are ways we can make some presentations, but if you look at if you look at, you can see my screen, right? Yeah. So these are the results that I have shown, right? So in AIMMS, to show to display your results, there are some other things that we have to do, which is going to take much of our time, right? So that's why. But if you look at this is a display of the results, the products, 2 to products 5, and then the total profits, which are the 2 variables that we have. So there are ways we can produce our results in bar charts, in pie chart and some other visualizations. So in that way, it's another programming entirely. We have to set aims, okay, do this, which is going to take much of our time. So, but because this is basically an optimization, that is why I restricted the programming to this.
Yeah, I don't know how to do it. I normally used to get the result and plot it. But that's just me.
Okay.
I used to just, when I did AIMMS, at least during my PhD, AIMMS was not very intuitive. So maybe there are advanced functionalities now. But rather, I would just take the various, I will plot it elsewhere, MATLAB or some others. That's what I used to do.
Yes, sir. That is also the way I did it in my PhD as well. But there was a time I saw a video on how you can you can produce bar charts, you can produce pie chart and graphs. So, but like I said earlier, it's another work on its own. It's not like it's automatically when you solve a particular problem, automatically you will get a result in pie chart and other visualizations. So you have to set the functionality. There was a video I saw maybe around 3 years ago or 2 years ago. I mean 3 or 4 years ago. Yeah. But as I said, it demands another work to do.
Thank you so much, Doc. Chima, I think I saw your hand up. You must ask a question. Are you speaking, Chima? You seem to be speaking, but we can't hear you. So I want you to use it for some of the extensions of your work. Okay. I don't think there are further questions. Yeah, so the most important thing is we learn by doing, right? Dr. Dimeji learned most of this things by doing. And then it's quite straightforward and easy. And Dimeji has done this. Uyi has also done it using robust. I know stochastic, Professor Badamosi and a few others have used it. So my point being now that the only way you truly learn how to use robust is if you actually do it. And we've listened and watched the doctor do it by himself, but we still have not learned it because you think you know it, but you don't know it. So we need to, within the next few days that we can, so that we don't forget, try to also get our hands dirty. Those that have not downloaded AIMMS, please download it, and then also try to learn it. All right, Dr. Dimeji, thank you so very much for taking your time. Thank you for sharing your knowledge with us. It's greatly appreciated.
Thank you for having me, sir.
Thank you so very much. So tomorrow we want to continue with any logic. Do you